Good afternoon, Daniel, and yes, good afternoon, Daniel, and good afternoon, okay, here I go. Good afternoon, Daniel. Good afternoon, Stephanie. Good afternoon, Jorgelis. Good afternoon, Luna. Good afternoon, Miriam. Miriam. I did it again. Good afternoon, Miriam. Good afternoon, Alyssa. Good afternoon, Jerry. Good afternoon, Yoon. Good afternoon, Jenna. Wait, Bella was coming in. Okay. Yes, it was the hunter moon, which means the moon right after the harvest moon, which means winter's come. Good afternoon, Ashley. Did I say good afternoon, Jenna? I think I did. Sorry. Good afternoon, Ashley. Good afternoon, Mariam. Good afternoon, Jorgelis. And why am I saying those names again? Oh, and good afternoon, Luna, and good afternoon, Sam, and good afternoon, Stephanie, and good afternoon. I think that's it. Why am I saying those names? You know why. Okay. Also, I feel like I'm still mispronouncing some people's names, but I won't. I feel like I'm mispronouncing Daniel's name, actually, because I've always had trouble correctly pronouncing the name Daniel. Okay, so you should tell me privately still if I still am. And right, I should be the one embarrassed, not you. Okay. We are going to start. I'm assuming you can hear me. I'm assuming that our left brain, right brain friend from the street is safely having coffee somewhere else today. Oh yeah, okay, you can. Great, thank you. Oh, here comes someone else. Great, thank you. Okay. Awesome. All right, so we're gonna get right to it. Just so you know where we're at. I want to and you can hear me. Right. Okay. I have not I want to go back to the homeworks soon. I mean, go back to talking about them, or going through them directly. They're not like abandoned forever, but one of the problems in the middle of homework 2 sort of motivated, or it was there deliberately to motivate this thing that we talked about yesterday. And I want to continue with that for one more class session. I'm hoping that you might recognize that what we're talking about right now is intimately connected to what you did or are doing in lab 3. Hopefully you see the connection. By the way, if whenever you were doing lab 3, if in the middle of it or when you were writing it up, if certain things seem really obscure or incomprehensible or out of nowhere, such as any references to K, the angular wave number, you would not be alone. That is a common experience. And it's a common experience in the middle of a lab to feel like, wait, I feel like I'm just doing something for the first time and I don't know what's going on. And I hope clarity comes later. Yeah, that is the nature. I mean, the fact of the matter is this is ultimately physics, not just math. So ultimately, we are driven by and tethered to our lab experience, whatever data we collect experimentally. And experimentation is just that. We never feel like we know exactly what's going on when we're in the middle of experimentation. We're not just testing hypotheses. We're also playing around mentally and trying to find handholds and footholds for our mind. So it often does go the case that there's that the lab introduction of an idea comes before the lecture introduction of an idea, because that is actually the way physics is experienced. But hopefully what we're talking about in these lectures right now might be shedding a little bit of light on at least what the meaning of that K is, that comes up in lab 3. So what we tried to do yesterday, Tuesday, was derive and then explain that equation that's in the middle of the page right now. Now, the equation that's right under it, you may or may not have seen in some other context, such as lab 3, but I've never yet said anything about the equation under it. That's what I'm going to try to show today, or I'm just going to try to connect or explain today. But where I feel like we are right now, at least as of Tuesday, is the equation in the middle of the board, Let me remind you what that is. Okay, first of all, just to remind you what that, so I should say. Right, just to remind you what that equation right there, that equation right there is one huge group of harmonic oscillators. The assumption of the way that that equation is written is the y-axis, the axis that we're calling y, is the axis along which each oscillator oscillates, right? So if these are masses on springs, if that's what we're picturing, then we're picturing a huge number of vertical mass spring systems, each one of which is going up, down, up, down, up, down like this. Or in, out, whatever the axis is that we're calling y. Frankly, it could even be horizontal, but it should, whatever the axis is that we're calling y, whatever axis along which each oscillator is oscillating, we're calling that the y-axis. But then we're arranging all those oscillators along an axis that we call x, and they're evenly spaced along the x-axis, right? But then even that's important. I should say, are arranged. Well, but they're all arranged equally along x-axis. And then what we're saying is that, and we're saying they're all identical oscillators, meaning that they all have the same omega. They all have the same k and the same m, whatever other physical properties determine their angular frequency. So, and they're all going to have the same, we're going to just declare that they all have the same amplitude. So they're identical oscillators in that respect. But the one difference among all of them is that they each get started at a different point in their cycle, right? And that's what we mean ultimately by phi, by phase constant. So they each get started at a different time in their cycle, like maybe the first one starts all the way at its amplitude position, but then the next one starts maybe at the equilibrium position or something, and then the next one starts at the amplitude position on the other side, something like that. Right. But not only do they each start at a different point in the cycle, but the difference in phase between the first oscillator and the second oscillator is exactly the same necessarily by design as the difference in phase between the second oscillator and the third oscillator, which is the same difference as between the third and the fourth, et cetera, et cetera, et cetera. So we have a whole horizontal line of oscillators that are all vertically going like, well, I can't. We have a whole line of oscillators that's going like, right, but much more smoothly than that. And as rhythmically and as regularly as you could possibly conceive. In other words, what this is the simplest possible, put it this way, and I think this is actually an important way to put it. I mean, with all of the conditions that I'm maintaining, like that they're identical oscillators, that they're equally spaced on the x-axis, that they're equally staggered in phase, or they're staggered in phase by an equal amount, by an equal step, right? All of this, at the end of the day, is a lot of words to insist on the idea that it's actually the simplest possible arrangement you could conceive involving multiple oscillators. It really is. And I'm almost tempted to write this down. Yeah, I'm actually going to. Okay, I'm going to write one more thing, and this is what I'm going to say, and I don't know if you can use that. First of all, I want to say sort of a weird point about what this equation is describing, right? And again, we spent all of Tuesday creating this equation. I mean, and when I say creating, well, I mean, it's not a definition, right? And it's not a discovery either. I say creation because I'm saying we set up a situation. We took our A omega cosine T plus phi, like the equation we had before, the solution to the harmonic oscillator. And then we made an arrangement in our mind. We said, what if we did this many, many times? What if we put an oscillator here, an oscillator here, an oscillator here? And we took that phi, that phase constant, and we tweaked it so that instead of phi being one number, it was a function itself, a function of position in X space, right? So we decided, we made an arrangement in our mind of a number of oscillators all staggered by a constant step in phase, okay? And we picture that in our mind. So we created it. But the reason I sort of have faith that you can follow what I'm saying, the reason I mean, look, it looks like a kind of a complicated equation. It's more complicated than a lot of equations we've seen before, and we're going to say a lot more about it. I don't know how you feel about it as an equation, but I'm claiming, and we are going to try to unpack it more and more. I mean, if you're still not comfortable with it yet, don't worry. But what I am saying is that equation is just a symbolic description of a picture that I'm actually fairly confident that most of you are holding in your mind as I'm talking. Like if you're paying attention at all, or you're paying attention Tuesday, I actually believe that you do get what I'm talking about, because I think you've seen it in life. And furthermore, even though I'm, as always, using all these words that make it seem like there are all these details that we have to track and all this complexity that has to be followed, the truth of the matter is what I'm really asking you to picture, what I'm really asking us all to describe, and why I think it's worth it, is that it's really the simplest conceivable ensemble. Ensemble means like group, collection, right? Like an ensemble of musicians. This is really the simplest ensemble of oscillations that you could possibly conceive of that would still be meaningful. Now, what do I mean by that? I mean, it's kind of an awkward sentence, especially a sentence that's meant to be describing something that's meaningful. But what I mean is this: if I asked you all to picture a whole bunch of oscillators that were all, if I were asked you to picture something one step simpler, right? Something that sounds like it'd be one step simpler. If I asked you to picture a whole bunch of oscillators that were all identical and all going up and down the exact same frequency, right? But I tried to make it really simple and say that here it's really simple. We're going to have a whole ensemble of oscillators, like 1,000 of them. They're all going to be stretched on the x-axis, and they're all going to go up and down with exactly the same phase, right? With exactly, in other words, the same phi. So they're all going to start. My stopwatch is going to start when they're all at the amplitude position, and then they're going to vibrate from there with the same angular frequency. Well, then what we would have is a whole bunch of oscillators going like this, up, down, right? Like together. And the truth of the matter is that, and you might say, well, that's even simpler. Why don't we just do that, dude? I mean, like that I can picture. And to that, I would say, well, at that point, if we were picturing that is even simpler, but that is not actually a meaningful group of multiple oscillators, in that if we had 1,000 oscillators all going like this, up, down forever, what you really have then is just one super wide oscillator, right? Like there's no sense in which there's no sense in which the group of oscillators then would have any meaning. It would not be a group in any meaningful sense. It would be one big long oscillator going like this, going like this, going like that. And now we can have that, but we already know all the math and all the implications of that. That's called a simple harmonic oscillation. I'm saying now, if we want to think, could we do something with a bunch of oscillators? Is there anything we could do with a bunch and actually have it be a bunch of oscillators, like actually take advantage of the fact that I actually happen to have 1,000 masses and 1,000 springs on my lab table, or I happen to have 1,000 molecules of, say, water sitting around, or something like that? If I actually wanted to put oscillation into gear with an ensemble, with a collection of oscillators, and I wanted to do it in any meaningful way, in other words, use the actual harmonic quality of each one of those oscillators, but in a group, again, kind of like an ensemble of musicians, then the simplest way I could possibly do that is what we're describing here. I'm saying, let's put them all out of phase with each other, out of phase, so that each one's doing something different, but out of phase in the simplest possible way, out of phase by a constant amount, right? That's what I'm using all this math to describe. Oh, okay. Yes, I'm going to pause 1 second, and and one last thing about, and I want to finish this page. But so I'm saying, if you ever you're picturing a bunch of things going like all down, and you're picturing the simplest possible pattern that you could possibly picture, but a pattern that is in fact a pattern, like that nothing changes, that there's a change, but there's no change in the change, right? Then you're picturing the thing I'm asking. I'm sorry, 2 more quick things, and then Sam's question. So number one, what I'm actually asking you to picture is, if you've ever been to, for example, not to be biased toward any certain borough of New York City, but if you've ever been to the Brooklyn Museum of Art, like on Eastern Parkway, they sometimes, or before COVID, they had a fountain, a bunch of fountains, and there are other fountains in the world that do this too. I think there's probably there's one in Lincoln Center, I think, of Manhattan. But like, they have a fountain that sometimes does this thing that I'm describing. It does it with jets of water. Now that fountain's really cool and really fancy because it does other things too. Like it has so many different patterns, but sometimes it does this pattern where it's like up, down, up, down, up, down. And I'm going to get Sam in a second, but let me just also say on number 2 here, like, so what you're picturing, if you picture this thing that we're talking about, you're picturing patterns in time that are then arranged into a pattern through space, right? You're picturing a pattern of patterns if you're picturing what I'm talking about. Sam.
Yeah, I think my question is just about the part that you just said, because I'm confused, because isn't y position, like that's what we were finding, the function is for a position?
Yes.
But is it in terms of, because there's 2 independent variables there, so are we like combining 2 different graphs essentially? Like, I'm confused about how to even think of the function.
Oh, no, that's great. That's great. Okay, and I'm going to and it's funny. It's something I was going to say something about that. Actually, I'm going to say a lot about that. But yeah, no, that's great. That's great. All right. First of all, to Sam's question, she is at the fact that she's saying, or I mean, the claim that she's making, and submit for points, blah, blah, blah. But the claim that she's making. Oh, and by the way, thank you for doing that in voice. So that's like a million different points. But anyway, yes, the first point that she's making is, I want to write right now. And sorry, as usual, and I hope it's clear. I'm not going to answer this question quickly. I'm going to answer the question right now. I am, but it's just good enough of a question and just relevant enough a question. I'm going to take a moment to answer it, and maybe even in more than one way. So the first thing that the sort of premise behind her question is, yes, absolutely. What we have here, this function, has 2 inputs and 1 output. That is definitely true. We have y, which is depending on both t and x. That is definitely true. So and by y, we mean the height along y-axis. By x, we mean position along x-axis. And by t, we mean time. So first of all, what Sam's saying, and I believe, by the way, if you think I was I was trying to say this Tuesday, but this is a big point. It's worth hearing 1,000 different times in 1,000 different ways. The first thing is, what we have here is a function of 2 independent variables. Those 2 independent variables, time and horizontal space, are each independent, as in acts like an input, but they're also independent of each other. So what this does mean in English is, we're saying that this is an equation that tells you, like, if you have a bunch of mass arranged the way I'm saying here, like if you have a bunch of oscillators, this equation says that for any given moment of time that you pick and any given place on the x-axis that you pick, and you have to pick both if you want that, but if you do, if you specify a moment in time and you specify a position along the x-axis, then this equation will predict exactly at what height you should expect to find mass. Like, there is one and only one height for any mass if you specify both time and horizontal space. If you just specify, and I'm going to be more detailed about that in a second, because the next thing she asked, or no, the thing that she asked is, well, wait, then how do you picture this on a graph? That's a really important question, because the whole nature of graphs, the whole nature of graphs is that they're two-dimensional. They're written on graph paper. So every graph in the world, and this is why every single experiment we ever do, every single physics lab ends in a graph. It's not a coincidence at all, because every lab that we ever do, what we're supposed to be doing is holding all variables still in the universe. Like, this is the scientific method, or this is what it means to separate variables and have a controlled experiment. We hold every factor, every possible factor in the universe constant as best we can. We play with one independent variable, like we play with one knob. In fact, let me get, this is so important, and really to everybody, and this is all about Sam's question, but let me tell everybody also, lest you think that it's just like now private, like she just, part of the reason I'm excited about her question is she happened to ask the thing that is like exactly where I want to go with this material next anyway. So this is not a digression. What I'm trying to say to her question, it's just easier to answer through the filter of her question. Okay, so I'm going to give an example to remember, just to like, what does it mean to do a physics lab, a physics experiment in the first place? Think classically. Let's just say that the hypothesis that I'm about to test, or let's just say the thing I want to find out in the lab is like, how much time does it take for objects to fall? Like, from giving, I want to find out, do heavier objects fall faster than lighter objects or not? Right? So what do I have to do? Like, I get rid of all other variables in the world. So I say, okay, if I want to test, if I want to see how much time it takes something to fall, and I want to see if heavier objects actually do or do not take more time to fall than lighter objects, then right away I start realizing, okay, so all I want to look at, is the relationship between time of falling and heaviness of object. I want to see if there's a relationship between the two at all or not. And so everything else I want not to be a variable, right? So what I do then to design this experiment is I would get a whole bunch of objects of all different weights, right? And maybe if I'm really being methodical and clear, and if I don't know if I'm going to find a relationship or not, I like lay them out on the table, and I put like a 1 gram weight and a 2 gram weight and a 3 gram weight and a 4 gram weight all out on the table, right? And I make sure that everything else about them is the same, right? They don't differ in size, like in volume or something like that, and they don't differ in like air resistance qualities, like they're all made of the same material. Let's say blah 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 blah, right? And then I take each one of these. So I'm holding everything else constant, right? I'm trying as an experimentalist, and this is like the gift of Galileo. If I want to see how time depends on weight, or whether it does or not, or how it does, right? Then I make sure there's no other variables no other independent variables besides like weight. And by that, maybe I really should say mass, but whatever. So I have all these different masses. And then what I do is I start dropping them from the same height, right? Like, I take a mass, like a 1 gram, and I take it up to a certain height, 10 meters, right? And I drop it, and I time the drop, and I write down into my table of values, like 1 gram, that's my independent value, my independent variable, like, is weight. I put that in the column, I put the value in 1, and then I time it, I see how long it took. And so then in this context, time would be my dependent variable, because I don't know what's going to happen with the time. That's what I write. And I write down the answer that I got from measuring. Then I go to the next weight. And please, everybody bear with me, because I know this is tedious, but I really want to make a point about how variables relate to each other, especially in this equation, and especially how to picture them when it gets complicated like this, which is Sam's question. So then I would go to the next one, right? Like 2 grams. And I would drop it from the same height as the first, and I would make sure that it has all the other same qualities, but now it's just 2 grams. So I drop it and I time it, and I write down the time in the table of values. So now, right, and I keep doing that, right? So now I have a whole column of weight values, and they're all like equally spaced. Like, I've deliberately tweaked the knob that's called weight. I deliberately went from 1 gram to 2 grams to 3 grams to 4 grams, and that's why I called it independent, because it wasn't dependent on anything. It was dependent on me, but I set up my experiment so that weight, it's really independent in the sense that once you see the left column of my table of values, and you see that I've written down like 1 gram, 2 gram, 3 gram, 4 gram, 5 gram, you could continue this experiment on your own. You would know then to put in 6 grams, then 7 grams, right? It's like, it's not dependent on anything. It's just a pattern, right? Then in the right column, we would see how nature responded. The very thing that I'm collecting data for, like the thing that I could not have predicted or known next. I would see what time it took each one of these masses to fall to the ground, right? It's how nature, so that I would see this other knob in the other column of the table, the knob that nature tweaks in response to the knob that I'm tweaking. The knob that I tweak is the independent variable. The knob, the response from Mother Nature is the dependent variable, right? Like very literal. And I write all these things down, and then I put them on a graph. I put them on a graph, and I always do, and I always can, because I necessarily notice this in any experiment we've ever done before this one. I mean, the real reason that Sam's question is a good one, folks, is that this is the first time ever that we have seen an equation of this kind. Like if you've only taken all of the classes in your life that you're supposed to have taken up to this point to be in this physics class, every single, even if you've taken 2 courses in calculus, but unless you just happen to have taken 3 or 4 calculuses because you felt like it, every single function you've ever seen up until this point is one variable depending on another. That is not a coincidence. And every single lab you've ever done ended in a graph, which probably made, if you're anything like me, then every single time you're like, oh my God, another graph. Is there ever an experiment I can do that does not end in a freaking graph? And the answer is no, there isn't. Because the whole point, so I'm going to go back to say, for every experiment up until this point has been modeled on the idea that that you tweak one knob, nature responds in another knob. Maybe even in our mind, sometimes we're thinking like cause, effect, or something like that. Like that's a little bit of a shady way to think, but maybe us do think that way. And then we can always make a graph out of it because we necessarily always have a table of values. There's 2 columns because it's one independent, one dependent. If there were any more, then we wouldn't have been doing experimental, we wouldn't have been doing scientific method, right? If there were any more, like how high we dropped them from, then that means we're doing 2 variables at once, and we're confusing the whole idea of trying to see what's the relationship between our input and nature's output. So then we would put those numbers on a graph. And in the case of this experiment, right, what we would do is we would literally put weight on the x-axis. So there's no rule that time always has to be on the x-axis or anything like that. We would put weight on the x-axis. We would put the time values on the y-axis. We would make a graph so that then from the scatter plot, we could see the shape and see if there was any pattern or trend that was recognizable in the way that nature linked these 2 variables. We're looking for the relationship in that case between weight and falling time, right? Now, in that case of the dumb experiment, it's not dumb at all, actually, but in the very simple experiment I just described, right? Hopefully, if you're following, you realize that, yeah, if you went 1 gram and then dropped it, and then 2 grams and then dropped it, and then 3 grams and then dropped it, hopefully you do know enough about physics at this point or whatever, or hopefully I'm making enough sense, that you'd realize that each one of those, it turns out, would fall at the same time, right? So if we made, and that's information, right? That's not like, duh. I mean, maybe it is to you now, but certainly when we look at this for the first time, it's what we're trying to find out. So then on the graph, what we would have no matter what, 1 gram, 2 gram, 3 gram, they all yield the same time. So we would get a horizontal line on our graph, right? Our graph would produce a horizontal line. And that horizontal line would not mean no information, and it would not mean stupid experiment. It would mean no correlation. It would mean that horizontal line that we just empirically demonstrated through all of our data, especially if we took a lot of it, that would be an empirical demonstration that it doesn't matter what weight you drop, all weights will fall at the same time, right? Now, bear with me again, that's not the experiment we're talking about here. That's just a classic experiment. But what I'm saying is in any classic experiment ends in a graph. And a graph is a relationship between an independent variable and a dependent variable. And a good experiment is supposed to reduce down exactly to that relationship, because what makes it a controlled experiment is that we have taken away all other variations, or at least we haven't taken them away. We haven't stopped the world. We haven't said nothing else is, we're not saying there are not other heights in the world. We're saying we're not looking at other heights in the world. We are deliberately holding the height of our experiment constant for all of these things. And we're deliberately holding aerodynamic qualities constant as we test each one of these. So what we're showing ourselves is a relationship between one changing thing and another. Now, this thing here that we have here today in front of us is a function of more than one variable. That has never happened before in a math class or a physics class. At this point, maybe it happened, but like it's the first time we're studying that. So the very first question, now finally, sorry, I don't know why I'm so excited, but the very first thing that Sam is reasonably asking about this, well, how the heck do you make a graph out of that? And the answer is you don't. She's right. You make two graphs out of it. And that's what you were trying to do in lab 3. You can't make, I mean, I suppose with computer model and rendering, you could make a graph out of this if you had a cube of graph paper to work with, or you're really good at computers. You could make a graph out of this. And I mean, there are such computer renderings, which are cool. You could, in principle, make a 3D graph out of this, but that's not what we want. That's not what we need. To answer Sam's question, what we do with this is do 2 experiments and combine the results into one. That's what you were doing in lab 3. What we do, in other words, so I'm still sort of answering her question, but in order to picture this, which is what she's asking, in order to make mathematical or graphical sense out of this, I want you, well, the concrete answer is we're going to make one graph. We're going to reduce this to true experimental form. We're going to take this phenomenon. We're going to create this phenomenon, or you did already. You create this phenomenon, and then you collect data from it in a scientific way. First, you hold X constant and take a bunch of Y as a function of T values. Let me say that again. First, you hold X constant, you pick a particular X value, and then you see what happens when Y varies in response to T, and you make a graph out of that. And then you start all over again with the same phenomenon. You start all over again in your data collection procedure. You hold T constant, you pick one T value, and you collect data to see how Y varies in response to X. I'm going to say that more concrete, but that is actually what you did in lab 3. It's why lab 3 is like very hard and weird at first, but very important. Let me back up and say, what's this phenomenon that I'm talking about? The phenomenon, this pattern of patterns, this simplest conceivable meaningful way to describe an ensemble of multiple oscillations. Well, an easier way to say all that, and I said it right in the last word of Tuesday, but what all this phenomenon is and what you did. Right, what this really is a wave pulse in every sense of the word. If you ever set this up, what you'd get is a wave pulse. And if you've ever seen a wave pulse, a piece of a wave, if you've ever seen a wave in action, it's ultimately describable as this. What I mean is, if you take a really long string, as you guys did, and a really long spring, a really tight elastic band, and like a tight, thin slinky. And one person holds one end fixed, and the other person takes one end and goes and shakes it up and down so that the thing wiggles, and you get like a crest over here, and then it falls down and becomes a trough. And then you get a crest over here, and then it falls down and becomes a trough. And then you get a crest over here, and it falls down. And so what you get is, what you visually see is something rippling, pulsing back and forth along this long slinky. Like you see bump, and then bump falls down, then over here bump, and then bump falls down to there, and then over here bump. So what you see visually with your eyes is like a bump of string traveling along, right? And I should do this right in front of you, but I can't. But I think we've all seen this somewhere in our life, or if you take along in the old days, like a long telephone cord, and you just like flick one end of it. Or for that matter, of course, a guitar string or a violin string or cello string, although there it happens so fast and it's so tight, it's sort of hard to actually see this with your eyes. But what you see is a bump in the string rippling from one end to the other and back. You see something moving horizontally. That thing that you see moving, I mean, assuming that this whole thing is lying along a horizontal axis, you see something moving along what we're calling the x-axis. And the thing that you're seeing is not a thing. It's a pulse. What do I mean by that? And I still want to go, I'm still have more to say about the whole SAM question and the graphs and everything. Wait, let me just, yeah, but I am actually, hold on, I'm going to bear with me again. It's all, what we're trying to show is how, on the one hand, how to look at one phenomenon from many different perspectives at once. But we're also trying to show, therefore, how one seeming phenomenon is actually many things at once. Or we're trying to show how many things that look like they are different things are actually one thing. I'm not sure. But what I'm saying is that I'm not done with the whole point about graphs, not at all, or the math of this. But what I'm saying is a collection of phase staggered oscillators is a wave pulse. Or similarly, what I'm saying is a wave pulse is a collection of phase staggered oscillators. Now, I'm assuming again that you've all seen wave pulses in your life. You know what I mean by a wave pulse, I think. And certainly the most vivid example, by the way, of a wave pulse actually is like if you ever go to Yankee Stadium or Shea State or whatever, it's Citi Field or something, right? And the whole thing where a bunch of people are in the stands and then they make a decision at some point for a whole bunch of people to go like this and then down, and then the people next to them to go this and then down, and then the people next to them to go this and then if you stand back and watch what's happening, or you know it goes on TV and there's a camera, you see a human wave go, right? It's called a wave, and it is a wave that goes through the whole crowd. It is a wave in every sense, in very much, and specifically in this sense of the word. And what do I mean by that really when I say, and it's a real physical thing. It's not like a wave, it is a wave. What do I mean by a wave pulse? Like, we're going to say a lot more mathematically about wave pulses. In fact, in some weird way, the rest of this course, in a way, is about wave pulses or things like wave pulses. Before we get all, and we're going to get very mathematical about them and very analytical about them. And we're going to get very abstract in our descriptions of them, because at the fundamental root of any wave pulse, any bit of wave motion, something very abstract is happening. Wave pulses are extremely common. Waves are everywhere in the world. Arguably, waves are more real than anything else in the world. And you've always heard about sound waves or light waves or heat waves, and you see waves all the time, right? And like Yankee Stadium waves, or like ripples along the string, or certainly ripples in the water, like in the ocean at the beach. And I think that most of us intuitively can recognize waves when we see them. But let's stop and really think for a second. What do I actually mean by a wave? Like, what is a wave pulse? What is one piece of a wave? Wave motion, what it is that when we recognize, oh, look at that wave over there. It's not just a wiggle. We're not just recognizing something that has a wiggly shape when we call something a wave. When we call something a wave, what we're recognizing is the lack of material ingredient. what we're saying is if we say, oh, look, a wave just went from there to there. If we're standing at Coney Island or Far Rockaway or at a beach, I mean, in other words, and we just like casually are watching the water and we're watching the ripples, the waves on the surface of the ocean. And those are real waves. I think that's as real as waves get. I mean, they're not like waves, they are waves, right? And we're watching them. And we just casually say like, oh, look at that wave. Oh, look at that big wave coming in. Boy, that surfer's really going to get it or whatever. And then if we just casually say, oh, I bet it's going to, oh, it's totally going to get in there before the surfer gets out of the way or whatever. Like we start making casual, intuitive predictions of the wave's motion in space and time, right? As though it were a baseball or something, saying like, oh, here it comes, here it comes. Oh my God, I can't believe how long it took to get to the sand and to break or whatever, right? And everything we're saying is reasonable. Like, you know, if you watch a wave pulse at the ocean, you watch a wave come in until it breaks, you totally could like go out and get a tape measure, measure where the waves, where you started paying attention to the wave, measure how far it had to travel, and you can get a stopwatch and time how much time it took the wave pulse to go from there to here, from location A, let's say, to location B, and you could time it and get it timing, and then you could calculate its velocity, and you could even predict, oh, this is its velocity, I guess next time it'll take twice as much time to go twice as far or something, and you'd be right. Okay, and you could do that with Yankee Stadium waves as well. You can say, oh, the wave's over there. Like, oh, here comes the wave. Oh, it's coming to section 8. Not section 8, that's like a type of housing, but like it's coming to like section 7. Oh, it's going to be in our section 6 any minute. Oh, here we go, it's my turn. In fact, I'd never even thought of this before, but in fact, the very fact that you actually can do a wave at Yankee Stadium or wherever, the fact that you can participate and you know when you're supposed to put your hands up, means your brain is watching the wave move and you are calculating how fast it's going from here to there, and you're correctly predicting when it's going to get to you. Right now, what's my point? Like, so what, Yaverbaum? Well, my point is the thing that you're watching traverse through space and time, the wave as it goes from location A to location B, necessarily, if you're calling that thing a wave and you're watching it, if you think about it, what makes it a wave is that you're watching something move from location A to location B, but there ain't no thing that's actually moving from location A to B, like literally no thing. Let me be more specific. If you're at Yankee Stadium going like this, doing this whole thing, all that's ever moving is human being. And again, that's a real wave. Or if you don't like that, what? Well, I'll say it. All that's ever moving is human beings. Human beings are moving. They're going up and down. They're creating that wave, right? There's motion, and the things that are doing motion are human beings. Or let's say in the water, if you think that's more scientific, like in the water, you're seeing a wave come to you and you're like, here comes the wave, here comes the thing. I can measure it in space. I can measure it in time. It's like real, yo. Like I'm not just like making up in my brain. It's coming to it. I could collect data from it. And you know, correctly know that there's a motion that you're observing. And the only things that are moving are water molecules, right? Water is like going up and down and sloshing around. But the thing is, there's no water molecule that's coming in toward you any more than is there a human being that's running around the stands when you make a wave. And yet, no, like when we say the wave is going from here to there, we mean something is going from here to there, but there's no thing. There's literally no thing moving from here to there. Like not just sometimes accidentally there might not be, but necessarily there isn't. If it's a human being wave going around Yankee Stadium, it's made up of only human beings doing motion, but no human being makes the trip that the wave makes, right? This is what's really important about a wave pulse. A wave pulse is an immaterial, like non-material, non-particle, non-particular type of motion. Wave motion from A to B means no identifiable, no distinguishable particle actually makes a motion from A to B. There are particles moving, but none of them is making it. A wave is intrinsically a dance, right? It's a bunch of particles, each of which is moving in a small neighborhood in such a specific pattern in its own neighborhood. And then we put all these little dances into such a specific pattern in space that we end up getting a ripple through space and time. And it is literally a ripple. I mean, that's a funny word in a way, but what I mean by that is, and I promise, I'm going to go back to the Sam's question and the math and the graphs and all that. But you can see why the math maybe gets funky or interesting here, because what we're studying when we study wave pulses, what we're studying is immaterial motion. We're studying a motion where there's no mover, there's no moving thing. In other words, in other words, to make a wave, we certainly do need material particles. We need things that are moving, whatever though. And please do write this down, because I am watching the clock and I want to get back to the math and Sam's question. But so the vast collection of things, of masses or water molecules or human beings, the vast collections of things that are going to oscillate each in their specific little neighborhood, their little zone, we call that vast collection of particles, which we totally need, right? We're not going to have a wave unless we have a bunch of little oscillators all oscillating in time and in space, right? That's what we're ultimately saying here. That collection of oscillators is called a medium. And what pulses through this medium is a disturbance, meaning a distortion, a change in shape. When we sent a ripple along the string in lab 3, when you just take a long string and you just shake one end and you see this bump, this crest, this pulse, this trough, whatever, move along. What are you saying when you say, oh, look, the wave pulse is moving, it's moving along to the other side? What you're noticing is some piece of the string that is misshapen. The thing that you're watching is like a bump or a trough or something. Now that's not a thing, right? I mean, it's not like a piece of string is going along. It's just that one piece of string went up and then went down. And then the next piece of string went up and then went down. So one piece of string was bent and then it was unbent. And then the next piece of string was bent and then it was unbent. And then so what you're watching is the bend, right? What you're seeing move is a disturbance, a distortion, a non-equilibrium shaping of the string. That's what's moving along, which is bizarre. Like it's not a thing. It's just a bad shape in a thing. And the whole larger set of things is what we call a medium. Okay. So from now on, when I say a wave pulse, I mean a particular, like I'm just focusing my attention on one particular disturbance and watching its journey through a medium. That's called a wave pulse. What's really happening behind the scenes is a collection of oscillating entities, oscillating particles, right? Now in lab 3, so I'm saying a lot here. I'm saying y equals a cosine omega t plus or minus kx is a mathematical description of a bunch of things oscillating at once in a pattern. I'm now also saying in English or in life, how that vast collection of staggered oscillators manifest themselves, how we experience that is as a wave pulse. And I'm saying a wave pulse is a totally scientific type of motion. It's a motion through space and time that is measurable, analyzable, predictable, just like the motion of a baseball or the motion of an electron or the motion of a rocket ship. Only what's different about it is it's not the motion of a baseball or the rocket ship or an electron. It's a motion of a non-material entity. A wave pulse is a motion in every scientific sense, but it's an immaterial motion. It's the motion of a disturbance. So if we want to study it then, as you did in lab 3, if you make a bunch of wave pulses on a string, then what you do is you guys took a whole bunch of, you made a movie of just simple shaking pulses along a string. You made a movie because a movie captures 2 axes of space and it also captures time. So you collected all the data in a movie. I mean, I guess you did it on a computer. It's a little bit different now. You did it on, but in principle, in the simulation, you had a movie of a thing shaking back and forth. So you had information existed on 2 axes of space and on the axis of time. But then how do you picture that? Or how do you picture this equation I'm saying, or what do we do with that? What you then did is you looked at the movie 2 different ways. First, you just isolate, oh, I don't know which one you did first. It doesn't matter what you did first, but in one example, one part of the lab, you just isolated a frame. You picked one frame of the movie, any frame you wanted. Maybe some frames were more convenient than others, but you took a snapshot of the thing, and then you looked at that snapshot and you looked at this. Well, actually, wait, I do want to draw this, but I'm going to get myself too involved. You hold on, I will draw in a second, but you looked at one snapshot and you looked at the wiggling of the, no, I will. What you did, right? What you did was first you looked at one frame, and like assuming that you had some pulse that was vertically pulsing, like a vertical bump or a vertical trough, that's like moving along a horizontal axis. If you think about it, and that's what we call a wave, what's necessarily happening in a wave is two relationships at the same time. And you can see those relationships if you look at them one at a time. If you just take one frame, if you just take, in other words, one moment in time, you see that at one moment of time, the string is arranged in like a cosine graph, right? Like some of the string is up and some of the string is down. And literally in that top graph, like it's just like, if you let your eyes move along the x-axis, you see that the string height is fluctuating along the y-axis. It's literally like, it looks like a cosine graph. That's if you just pick one value in time, and it could be any, right? But if you pick one value in time and just take a photograph, you see that wiggle and that wiggle shape. Now, let me also say that a lot of people like think that wiggle shape is a wave. That wiggle is not a wave. That wiggle is harmonic oscillation, or that wiggle is a wiggle. What's that alone is just a shape. Like I mean, if I arrange a bunch of dominoes on my desk in that curve, that's not a wave. That's just a wiggly shape, right? But because that was just one moment in time. At this also, though, if I pick one value on the x-axis, as you did in lab 3, if I just pick one place along the x-axis that's sort of maybe convenient, like maybe near some sort of like clear vertical edge that I can use in my mind as a y-axis, or maybe I even put a ruler in the movie or something like that, and I just focus all my attention on, and I use Logger Pro or something to arrange red dots. If I focus all my attention on one horizontal space and I just watch what's happening to the string's height as time evolves, in other words, if I watch a movie of just one part, then I see dots. I see the height of the string going up and then down and then up and then down and then up and down, just in that place, right? And if I slap those values onto a scatter plot, onto a graph of y as a function of t, holding x constant, right? Then I also get that cosine graph, right? What we're saying is a wave pulse is cosinusoidal oscillations in time, like y as a function of t. Any one bit is going up, down, up, down, up, down in a cosinusoidal simple harmonic fashion. That's if I hold any x value constant and look at the y-t relationship, I get a cosine. But also, if I hold any t value constant and look at the y-x relationship, like the shape of it is a cosine, right? So I'm having cosinusoidal oscillations in space and in time at the same time. That's a wave pulse. And again, not to beat a dead horse, but to go all the way back to Sam's question, it is one dependent value, y, like height of mass. I'm sorry, yeah, it's one variable, y, depending on two independent variables, t and x. We can't picture that all at the same time on one graph. We've got to look at it as two different graphs, two independent graphs. And the two graphs really are independent. They're not affecting each other. They're just both happening, but they're happening together at the same time. So what emerges is this beautiful phenomenon where you can have motion from here to there without anything actually moving from here to there. This is a fascinating thing. This is how we send sounds to one another, like on accident, but then this is also how we send information to one another on purpose, like through the internet, through radios and stuff like that. Like wave motion is a mind-boggling topic in a way if approached like with a positive attitude, because it is motion without movers. And yes, there are always, like, there have to be movers, there have to be things going up and down, but whatever things are moving in order to create the wave are not moving in the way that the wave is moving. And that's why we call all those movers a medium. We say that a wave pulse, it doesn't travel. Baseballs travel, rocket ships travel, electrons travel. Wave pulses propagate. What do we mean by propagation? Oh, we just mean travel. When we're talking about wave pulses, we're just we have a whole different vocabulary just to highlight and reinforce and remind ourselves constantly that when a wave pulse goes from here to there, something immaterial is going from here to there. It's just a disturbance in a larger medium of material particles. Now, I only have 10 minutes. I hope that sort of answered Sam's question. It is what I wanted to say. It is the point of lab 3, but now there's a math thing there's a lot more math I want to do with this. I know I've got 11 minutes. So I'm going to say, it's like, what do we do? So now this is the first time we have a function of two variables or of more than one independent variable. How do we deal with that? Like, what can we do with that? Like, for example, how do we look at rates of change? For example, how do we look at derivatives of functions of more than one variable? Like, again, to answer Sam's question, like, how do we look at graphs? We make more than one graph and we put them down. But how do we look at derivatives? Same thing. Okay, no problem. Direct chat person. Got you. No problem. No problem. Thank you for coming. Okay. All of this, sorry. If we're picturing a graph, or if you're picturing a function of more than one variable, if you want to know at any given moment, what is the infinitesimal rise in that function? What is the infinite, or in this case, for our wave pulse, like if at any moment, if any piece of our situation, we wanted to know what is the infinitesimal change in the height of mass pieces in this string pulse that we created. If we want to know what's the infinitesimal rise in the dependent variable y, we believe that the two things that contribute to y are time and horizontal space x. We believe that they are independent of each other. So what we're believing when we do this whole experiment, when we pick one moment in time, i.e. take a frame out of the movie, just think of a photograph, one moment in time, and we look at how y is varying as a function of x, what we're doing is holding time constant and just looking at the way in which y depends on x. We're not saying that t is a constant for this phenomenon. We're not like literally like stopping the clock of the universe. We're just saying, what if we pick one value of time, hold it constant in our mind, and just ask, how is x driving y? And similarly, we can hold one value of x constant in our mind, just pick a value of x and just say, for that given x, how is t driving y? It's the scientific method, right? It's not saying that everything in the universe is constant. It's saying what happens when we hold everything constant and only pay attention, only isolate the seemingly unaffected, seemingly independent relationship between two variables. So we can do that. We do that in this level when more than one independent variable is producing a dependent variable. We can take what are called partial derivatives. So from here on, so now I'm teaching something. This is like a thing. I'm not expecting that you've seen this before. I mean, you might have, but I'm saying it now for the first time. So like, please write it down, and please don't like fog out because you think this is all of a sudden something that you were supposed to know, didn't, and blah, blah, blah. No, I'm saying now, I'm introducing a new piece of notation, that scripty, weirdy little lowercase t that sort of looks like a lowercase delta or something, but isn't, or looks like some Celtic letter, I think. That from now on, we're going to read that as partial. If you see scripty y over scripty t, it means the partial derivative of y with respect to t. It means the rate at which y changes as a function of t, assuming that everything else is hold constant. So what we're saying here is the infinitesimal rise in the y value for this function is the sum. It's like how much, we're basically saying the amount that y rises at a moment is how much it rose due to what we found on the t graph, plus how much it rose due to what we found on the x graph. We're saying that the full derivative of a function is the sum of its two independent partial derivatives. And it allows us to take a partial derivative of something really means to differentiate it with respect to one variable while holding all the other variables constant. It's what we do to multivariable functions such as this one. Now, I have 5 minutes. I'm going to quickly do it, as that may sound obscure, but I'm going to do it now to our function that we have. And this is where we're going to end. And bear with me if I go, I'm going to try to go a little bit fast here, but we have let's call it. Okay, we have this function. If I want, I'm going to take, and I'm going to do this again, and bear with me. We got 4 minutes. I'm going to do, and this is where I wanted to get to. This is where we're going to end anyway. But say I want to take the partial derivative of y with respect to t of this function. And again, this might seem familiar to you from lab 3. Hopefully, this will make it clear if you did it. It means I'm going to treat t as the variable. And I'm going to, even though x is a variable and t are like, even though x and t are both actually variables, just like in an experiment, I'm going to hold one constant while just seeing what happens to the other one. So partial y, partial t means I'm going to pretend for a moment that x is constant and treat only t as the variable. So if I do, so I'm going to get this. Right. And just for kicks, let me do that again. I'm going to do it a second, right? So in other words, the omega came out from chain rule, but the k did not come out. This goes back to like 3 days ago. The k didn't come out because I'm holding x constant. Notice this is, and I know that I'm allowed to because it's a partial derivative. Notice the weird scripty d's that I'm now using. I could even do that again. I could take a second derivative. Where's he going with this? I could take a second derivative and the same thing would happen again. Right. Okay. And I've got 3 minutes and I'll just leave that there. And I'm going a little fast again. Tell me right after if you need me to go, but I'm going to turn the page here. I'm going to, and if you have to act and I have to turn back in a minute, I will, but now I'm going to now take partial. I'm just reminding you what the function is. It's right here. I'm going to take partial derivatives now with respect to x. It doesn't mean that t isn't changing. It's just now I'm looking at a different thing. It's like setting up a different graph. It's like collecting a different set of data from the same phenomenon. I'm going to go, what's dy dx? Well, here, x is a variable. So here the k will come out, not the omega. And I'll get this. And then I could do that again. Why? Because I'm always like interested in second derivatives because this is physics because f equals ma. So I do it again. And I get this. Right. So first of all, those are just examples of taking partial derivatives. You can do a third derivative, a fourth if you want, but partial derivative means you look at the rate of change of one variable with respect to the other, holding the other constant. So we're always still doing scientific method. We're looking at a function of many variables, but we're always just treating one pair of variables at a time. But with the 1 minute left, just check this out. That looks very similar to what's on the other page, right? It looks very similar. In fact, I can say, again, bear with me. If you have to go right now, go. Otherwise, I'm going to go like 1.5 minutes over. I apologize if you have to go and get this from the notes, but just bear with me. Notice I've got the second partial derivative of y with respect to x has blah, blah, blah times cosine, and the other one has blah, blah, blah times cosine. So I'm gonna rearrange each one and solve for the cosine thing. I'm going to say this again with 1 minute. So. Right, the two look very similar. So I could set them equal to each other, right? And I'm just about, that's where on the last line here, I could set these two equal to each other because they're both equal to the cosine thing, right? So I promise, thank you for bearing with me, but I set them equal to each other. Right, and the negative a's cancel out. And on the very last, this is the very last thing I'm writing, but and if you've bared with me this far, it's totally worth it. Thank you. I think on the very last page, I just multiply both sides by k, and I say this. And this is where we're ending this, which was the equation on the very first page today. This is the wave equation. This is a partial differential equation. It's a differential equation, just like our harmonic oscillation thing was a differential equation. In fact, the left side looks very much like it, but the right side looks different. This is a second order partial differential equation that describes all waves. Anything that satisfies this equation is a wave. Anything that is a wave is describable by this equation. This, if you look at it, you compare it to the thing that we've been churning and burning every day. This is simple harmonic oscillation happening in time and in space. We will unpack this more next week, but this is the wave equation. This is a collection of phase staggered oscillators. Thank you for waiting for the extra 2 minutes. Sorry about that. I'm done. Have a good day. Yes, have a good day. And I'll hang for questions if there are any. But yes, have a good day. Thank you for me. Okay. Have a nice weekend. Yes, have a nice weekend. Awesome. Thank you, guys. Okay. But yes, no, that's totally, I expected it actually. Hold on.